Welcome everyone to the engineering course we offer called Digital Processing Engines. So when we say processing engines, especially the word digital, what we mean by is shown below, that we are talking about microcontrollers, microprocessors, DSPs, FPGAs, SoCs. So it's a series of courses we offer, engineering courses we offer, and uh, it's basically uh, an advanced digital logic circuits or systems design related courses. Anyone interested in knowing the details about the words in this title, it's highly recommended to please visit Cambridge or other similar quality resources to find out the historical journey of these words like digital engines, microcontrollers, microprocessors. DSPs stands for digital signal processors, and FPGAs stands for floating point gate arrays. So let's go to the next slide. So we offer these courses under Quantech Field Institute, an affiliated organization with Soft Galaxy Technologies Inc. Anyone interested in knowing the details, highly recommended to please visit our LinkedIn profile to see what we have done and what we do. Anyone want to connect with us in taking these courses, please send us an email to info at HS stands for Humanities Serving Clouds.org or softgalaxy.hsclouds at gmail.com. One of the key things what we believe in as an organization and professionals is that there is no shortcut to glory. It means you have to work hard, you have to learn the basics, and you have to follow the right um, processes in achieving your objectives and to be successful in a particular field of your choice. Okay, let's carry on. So this particular course, the potential career options will be that you can be a digital circuits and systems designer, and that's a very heavy responsibility. It means that you need to have a very much, not only a clear concept on basics of analog digital electronics, along with this advanced level of understanding on advanced digital logic designs, before you can not only the knowledge but also the experience before you can be part of job responsibilities like digital circuits and system designer. Other career options will be you can be a digital signals processing related job responsibilities you can perform, and you can be a firmware developer. And if you have taken our prior courses, you do understand what it means by firmware developers or embedded developers. Basically, low level ability to program smart devices, again, like microprocessors, microcontrollers, and so on and so forth. So, what are our course objectives? The course objective is to establish firm understanding in designing and working with advanced digital electronic circuits and systems. And that's why the title of the course is Digital Processing Engines, because most of the time when we talk about designing a system or a product nowadays, it's a combination of all those keywords, like microcontrollers use, microprocessors use DSPs and FPGAs or SoCs. Depending on applications requirement, we select those components and we use it for our desired needs. And if you have taken our prior courses, please, or if you have not, Highly recommended to please download the slides. The link is given in the video description below to see all these YouTube videos. And the reason of showing you these YouTube videos is because just to emphasize that this particular course, what you will learn is directly utilize how in the industry as of now. So it's you those technologies or the knowledge of uh, digital processing engines, that knowledge has been utilized in manufacturing industries like manufacturing the cell phones, or in robots manufacturing or using the robots for the desired needs, self-driving cars, or the Amazon order fulfillment centers, robots, or whatever the processes, the automation processes they have in order to achieve their system objectives. Here's the required lab resources. We expect that you have an AMD Xilinx board or kit on your site. We highly recommend that because that's what we'll be focusing on. AMD Xilinx is one of the most popular FPGA SoC vendor known as of 2023, and that's why we like our students to work on with their kits tools. But if you don't have the AMD Xilinx board, or you cannot acquire it easily, any of these boards like others like Intel Quartus, another very well known FPGA SoC vendor. So if you have the kits from any of these two, Intel or Lattice Semiconductors, or if you don't have even these two, any of the kit you have available, easily available, low cost, if you have it, we can help you learn the concept we discussed here using that particular kit. So no worries on that, but it's highly recommended to go with AMD Xilinx as of 2023. I think having a kit, an FPGA kit, is sufficient, but these other three things are good to have just for to have a kind of uh, nice lab environment, because most of our labs will be focused on only using a particular selected FPGA kit, and most of the time the kit comes with the power supply, so you don't need a power supply or multimeter or oscilloscope, because we can implement a digital logical analyzer within using AMD FPGAs or AMD Xilinx toolchain. Okay, so let's go to the next slide. So here's the distribution of marks. If you have taken our prior courses, it's pretty standard. 10% is lab assignment, which do include the lab work which we will assign to you. So 5% of that will be before the midterm. We will give it to you, and the 5% will be before the final. The lab work will be 20%. You'll be testing on it before the day, on the day of midterm and on the day of final. So before the midterm, you will be given a 1 hour lab exam, and before the final day, you will be given a 1 hour lab exam, which is 10% weightage each, 10% for the final, 10% for the midterm, and there will be a half an hour, 1 hour break before you will get the actual midterm as an exam, or the final as an exam, which is 40% for the 40%, and it's an hour and a half long exam, and midterm is a 30% an hour long exam. We will try to do. Our plan is to do industrial tours to give you a practical knowledge and experience of how the concept we learn in this particular course are utilized in the industry, which will be greatly beneficial for you to learn in relating to these courses. Okay, so let's carry on. So let's talk about microcontrollers. When we talk about processing engines, again, because we are processing digital information, digital data, so microcontrollers are one of the low power um, chips, ICs, you can say, integrated circuits, very commonly used for many applications globally in the industry, for industrial or consumer applications. This is a very well known microcontroller from Texas Instruments, in short TI MSP430. And as you can see, if you download their data sheet, this is one of the block diagram you will see in that particular data sheet. So you can simply Google or the MSP430 data sheet, and when you open up that PDF file, you will see this as one of the block diagrams. And what is our intention? Is to give you a clarity on every block, every common block. So not every specific block. So for example, in this block diagram, so you will know, so CPU is a central processing unit where all the processing happens. The JTAG interface is also one of the common blocks. But SPI by wire may not be a common block like in other microcontrollers. So our intention is to give you clarity on what is a flash block, a RAM block, an ADCs, and analog to digital converter, a 10-bit. These are the op amps. So the common blocks which are common to microcontrollers from other vendors, like it can be Intel, it can be ST, it can be Analog Devices, or there's so many other microcontrollers or IC manufacturers globally, they manufacture. But our focus during this course, when we'll be discussing microcontrollers, microprocessors, DSPs or FPGAs, is to focus on the most commonly used blocks for that particular IC, in order to give you the required information, concepts to be clear on, which will help you select, when you work in the industry, it will help you select the right IC for the requirements you have at your hand. Okay, so let's carry on. So again, these are microcontrollers. This is PIC from Microchip, PIC F877 series or 7X series of microcontrollers, and as you can see, it has a lot of blocks, and we will discuss that during the course, the most commonly used blocks in different microcontrollers. Okay. So similarly, this is from STM32, ST Microsystems, STM32 microcontroller. What you see here, it's a block diagram taken from their respective data sheet. Okay, let's carry on. So this is when we will be discussing microprocessors. We will discuss what is a RISC type of a microprocessor, what is a CISC type of a microprocessor, and nowadays when we talk about microprocessors or motherboards, in general public, they talk about cores. So we will discuss what in a microprocessor, if there are multiple cores, how they work, how they enhance computing performance, and then we'll discuss about storage, like memory, SRAM or DRAM, or some other type of memory. So we will learn the differences among different type of memories, their pros and cons in use in different system architectures. Okay, so these are some of the concepts we will learn when we will start discussing microprocessors. To enhance microprocessors performance, there's a concept we call as caching. So we will learn about cache. This is a hybrid cache architecture shown here. level 1. L1 stands for level 1, level 2, level 3. So we will go into the details when we'll be discussing memory technologies, and related concepts to enhance overall performance computing of a certain computing environment or architecture. Nowadays, in-memory processing is a very popular concept, and there are so in-memory performance. What it means that rather than because all the processing happens on a CPU, central processing unit. In this case, like there are four cores, so all of those are basically processing engines. So in order to do any calculations, um, the processor has to go to the memory, fetch the information, and then process. So the idea is, because it takes time in going, fetching, and processing. So rather than fetching the information from the memory, why not do the processing where the data is? So that's what it means by in-memory processing, and we'll learn about it. Pipelining is also a very important terminology. When we talk about enhancing processing power in a microprocessor, DSP, or other architectures, and we will learn about what pipelining is and how it is utilized when in microprocessors, DSPs, or other architectures. Okay, so let's carry on. So here's a block diagram of digital signal processor. So when we will discuss DSPs, I'm just trying to see that this particular block diagram is taken from where. Most likely I have taken this from a Texas Instrument, one of the Texas Instrument DSP. Yeah, right here. So it's a 67 series Texas Instrument DSP. It's a floating point processor. That's a block diagram. As you can see, there are so many different. This is an I2C block, timers, general purpose I/O, some serial external memory interface, and this is the CPU side of it, which has multiple data paths, cache. Yeah, so we will go into the details. Level 1 cache, as you can see here. We will go into the details when we'll discuss DSPs and discuss the most commonly used blocks. So when we discuss about microprocessors or DSPs, to estimate their computing performance, these are very well known performance units, flops or MIPS. Flops is floating point operations per second, and MIPS stands for millions of instructions per second. So we will learn about it, what a flop is, what a MIP is, in this particular course. Again, this is the DSP, and this is showing an application of a digital sound receiver, surround receiver, and a block diagram of it using 6713 DSP, and that's also taken from a Texas Instrument website. And so we will discuss such block diagrams, the applications used when we'll discuss microcontrollers or microprocessor, DSPs or FPGAs, in order to give you kind of a practical knowledge required, which we intend you to carry on after completing this particular coursework. And again, this is another DSP. Blackfin is from Analog Devices, a very well-known, like an industry established DSP. And this is a functional block diagram taken from the Blackfin's data sheet. And as you can see here, we have a DMA controller, level 1 data memory, and again these are the watchdog timers, real-time clocks, timers, SPI bus, or a SPI port. We will learn about what a SPI port is, what a UART is. Most likely you already know it, but anyhow, we will discuss all the serial communication protocols we use when we will discuss all of these, like microprocessors, microcontrollers, um, DSPs, and FPGAs. So here's when we'll discuss FPGAs. FPGA stands for floating point gate array, and SoC stands for system on a chip. FPGAs, SoCs, just like in English, there are a lot of FPGAs and a lot of SoCs. When we'll discuss these ICs, we will look into these block diagrams and understand what they means. This is taken from AMD Xilinx Versal datasheet, and that's the Versal device layout. As you can see, it's a very expensive FPGA SoC. As you can see, it has a processing unit, and it has a PL fabric, a DSP, and memory. And we will learn more about it. It has, as you can see, it has serial transceivers on both sides of the, or basically, in this particular block diagram. There's another block diagram from the same data sheet. As you can see, it's a programmable logic, and we will learn about it, what it means by a programmable logic. It's basically a logic which you can reprogram to implement a particular digital design. That's what a programmable logic do. Processing system is just like your microprocessor. In this case, as you can see in the block diagram, it has an APU block and an RPU block. An APU block has 2 cores, and RPU block has 2 cores as well. And it has PCIe kind of buses which you can utilize, the serial transceivers. And we will learn as we go, memory controllers and this and that. We'll learn more about as we progress in this particular course. Important thing here, as you can see, there's a security unit as well. So, and all the popular microcontrollers, microprocessors, DSPs or FPGAs, you will find security blocks there, or security features there to make sure that your firmware, your design is properly secured. Again, so this is another block diagram from another very well-known vendor, Intel. Intel Area 10 devices of FPGAs, and here's the block diagram. As you can see, it's an adaptive LUT. LUT stands for lookup table. So again, this is where you can implement your digital design, and there are ports. It can take either route, and yeah, we will discuss that in detail, and I'm just trying to give a high level kind of an understanding that what we will be doing during this particular course work. Again, this is a transceiver, Area 10 transceiver block architecture, and as you can see, it's showing the transceiver serial links, high speed serial links with a common bus, and connected with the FPGA fabric. So this is in an FPGA or SoC, there is a hard processor system. We call it, as in short, HPS. This is also, I think, taken from the TI, one of the TI AMD Xilinx, not TI, AMD Xilinx data sheet. So this is showing an HPS block diagram of an ARM Cortex-A9 M-core processor. As you can see, it's basically is like a CPU, which is it's not. So we will discuss that, that there are chips where there is, what is the difference between a hard processor system or a soft one. A soft processor system like Microblaze is all software that which utilizes the fabric, the logic fabric to be implemented. But hard means that it's already there as a chip on the within the chip of an FPGA or SoC. Okay, so that's what it means by a hard processor system. Two cores, again, the relevant blocks, and we will go into the details in understanding all the most commonly utilized blocks on FPGA or SoC chip. Similarly here, as shown before. In this course, so these are the two most popular HDL languages industry and educational institutes use in running their business. HDL stands for Hardware Description Language, and so in this particular course we will learn about both these languages, VHDL and Verilog. So as you can see, this is a very good example what our intention will be. That let's say that we will implement a simple latch. So you don't have to go and we will discuss every single line in detail during the course. But just as an example, as you can see here, if we will implement using VHDL a latch, what is a latch? It's going to store information, whatever is at the input. So in this, you have 3 enable lines, 3 inputs, and 1 output. So as you can see here, whenever one of the input goes high, the output is stored. Okay, so that's what happens. If enable 1 goes high, the output will be stored on the A1 port, so on and so forth for A2. If enable 2 is high, enable 3 is high, so A3 will be stored at the output. So let's say we will implement a latch or any other solution to a problem using VHDL. So there maybe we will assign you as an assignment to implement the same using Verilog, or vice versa. If you will implement it in Verilog, you will be given the task to implement the same in VHDL. So we will cover both of these languages. We want to make sure that you have enough information, enough knowledge to be comfortable in using both VHDL or Verilog in this particular coursework. Let's carry on. So as mentioned right at the beginning, our emphasis is to use AMD Xilinx toolchain. So this is the Vivido, one of the very popular tool from AMD Xilinx, used to program FPGA's PL programmable logic fabric. And so we will be using this particular tool. We'll be using Verilog or VHDL using this tool. We will also be using their block diagramming feature, which is very powerful. We will practice and give you knowledge on that as well. Having this knowledge, I think, will be very, very beneficial in the industry. And we will also explore the PS side of the tool from AMD Xilinx, which is called VITIS. So we will explore VITIS side of the tool chain from AMD Xilinx. And this is a very good, really like this. As you can see here, VITIS is used for so many industrial applications. And but don't get afraid by just looking into this cool diagram. The main focus will be that we will be working with VITIS, and we will be discussing VITIS HLS, high-level synthesis. So, but there are many more applications. This is what we're trying to. I'm trying to show you here that what the AMD Xilinx toolchain can achieve. It can work with these very popular kind of tools. It can work with the MATLAB Simulink, and if time persists, maybe we'll try to show the connection, but we'll see how that goes. Okay. So this particular slide shows the FPGA field programmable gate array market segments globally. This is compound annual growth rate CAGR, compound annual growth rate. So what is the annual growth from 22 to 28? And as you can see, it's growing at a very fast rate. These are the market segment: SRAM segment, less than 28 nanometer segment, low range segment, high range market segment. So they are growing, I'll say, exponential growth. So in 2021, the capital annual growth rate was greater than, in total, 12%, which what it means by $6 billion by 2021, and it's expected that by 2028 it will exceed $14 billion. So as you can see, it's an area of the market you want to be in. You want to have a strong footing. If you want to succeed in this particular area, you need to have a much clarity on the basics before you can work with the advanced feature in digital logic and system design. Again, there's another graph of field programmable gate array. Compound annual growth rate is 8.32%. 2023 is roughly around $8.7 billion. By 2028 is $13.07 billion at the time of the study. And so I put this snapshots from the web here just to show that how fast this particular market segment is growing, and secondly to show the major FPGA SoC IC manufacturers globally. These are the major plays. AMD, Xilinx, we already discussed. Intel, we already discussed. Lattice Semiconductor is another very strong player in this market segment. QuickLogix, Acronix is another one. But I also recommend to look into other companies. Do not leave other companies, the growing companies like Galvin, Semi, FNX. And if you just Google the FPGA chip manufacturers, you will find, and I encourage you to look for companies who have their market base in USA, and because not necessarily that every time you need to work with these vendors. There is a possibility for small scale applications that the other solutions, competitive solutions, may be better. Okay, let's carry on. So Microsemi is another one, like an FPGA chip vendor. So the preliminary course requirement for this course is mathematics and physics, a decent knowledge of the completion of high skill, very good understanding of the digital logic theory and design. So at least at least 2-3 courses before you take a course like this, and you also have a basic understanding of on programming in C or any other programming language. More emphasis on C, Python or C++. If you know the programming, that how a logic is programmed, it will greatly help you learn the other the VHDL or Verilog language, because logic and understanding the logic, how it works, is really beneficial in this particular course. So these are the references. They are ever growing, so don't think that they are a complete list here, but we will share all the references we follow during a particular coursework. Okay, so thanks for attending this session, and we'll look forward. Take care. Bye.